Shimizu is a professor in the chemistry department, Faculty of Science at the University of Calgary. You can introduce yourself because I don't have.
Okay, that's fine. All right, thanks Ken and Trevor for the chance to come and participate in this. So I'm going to talk about a new type of nanoscale porous material that has applications both as a sorbent material and, as I'll talk very briefly about at the end, as a fuel cell membrane. Let me just figure out this point. Okay, so that's the pointer, and okay. So this class of nanoscale compound is called Metalorganic frameworks, and it's actually a very descriptive name. But to give you an idea of what I mean by that, if you consider a metal oxide, so here this could be any mineral. So here blue is just a metal and red is an oxide. So this would be representative of probably thousands of different compounds. If you consider that as a metal oxide, then what a metal organic framework is, it's basically replacing the oxide with an organic molecule. So here, I've done this schematically where the metal ions are still the same, but we've replaced just the red sphere with an organic linker. And you might think, okay, well, you can maintain the same type of structure, but if you spread this out, you should generate a pore in the compound, and that's exactly what happens. Okay? So this actually seems like a very simple idea. For the longest time, though, people didn't think that the bonding, when you go to an organic molecule instead of an oxide, you cut the strength of the bonds in under half. So people didn't think this would be stable enough. But it turns out people were wrong. So this is actually an X-ray structure from a crystal. So if you have a crystal, what that means is that all the molecules in it are aligned, and you can zap it with an X-ray and you'll get a map of where all the electrons are. So if you know where the electrons are, you know where the atoms are. So this is really a picture of the molecules. So you can see here's a phenyl ring, a phenyl ring, a phenyl ring. Here's a metal cluster. And the big yellow spheres here represent the actual hole in this compound. Okay, so this has been an active area for about 10 years. So much so that last year they had a special issue of a review journal devoted specifically to this. So the big advantages here, so let me just explain as far as gas storage, why this type of material, an adsorbent material, is good for gas storage. So let's say if I had a gas cylinder here, and I said we could pressurize it with some gas and you can fit a certain amount in. If I said you could put something else in that cylinder before you put the gas in that would allow you to put more gas in, that might seem a little counterintuitive. But that's exactly how these materials work. And so my analogy for this would be like, let's take this room. If we had, say, 5,000 3-year-olds outside, and we had to try to herd them in here, we could try just brute force and just herd them all in here, and they'd be running all over and bugging each other, and it would be, I have a 3-year-old, it would be a nightmare. Okay. But if before that, we actually divided this room up into little cubicles and said, everyone go into this room and you have your own little cubicle, and everyone ran to their cubicle. They wouldn't see each other. So it's an exact analogy, because what happens is their kinetic energy would be reduced, and you could actually get a lot more of them in a lot easier. That's exactly how gas storage works in these compounds. Okay, so what you want then, so I mentioned they're ordered. So that's really nice because for two reasons. First of all, it allows you to get a picture of the compound and you know exactly what you're working with. The second thing is all the pores are the same. So you don't have macropores, mesopores, micropores. So you get very uniform performance in terms of gas storage. Okay. The other thing is they have very high surface areas. These are the high surface areas, low density. So low density translates to they're not very heavy. Okay. And so these are the lightest crystalline materials that have ever been reported. They're on the order of gels. All right, so I mentioned you'd like high surface area. So a lot of times people think, well, if you can make a porous compound, making a big pore is better, something macroporous. Well, if you take this, here's the internal surface area, but if you actually partition that into for smaller squares, you would actually increase the internal surface area dramatically. Okay, so smaller pores are actually better. So this is where this nano theme comes from. You'd like the solids interior to be accessible. So if you picture a honeycomb, the gas can only get in from the ends of the honeycombs versus something three-dimensionally porous where if a pore collapses, it's not the end of the world. You can still access that space by two other directions. And also the shape and the chemical nature of the pore. So going back to the 3-year-old analogy, this would be being able to tune the chemical nature of the pore would almost be like being able to put a toy inside your cubicle for this to attract the gas molecule. Okay, so how do you get a gas to stick to a surface? So CO2 scrubbing right now, you bubble it through a solution of amine. So here's an amine, there's a CO2 molecule. And what you do is you form a covalent nitrogen-carbon bond. Okay, so this is a strong interaction. It is a chemical bond. Those electrons are shared. And so a third of the number I always hear is roughly a third of this energy of this entire process is to regenerate your amine, to reverse this reaction and break that nitrogen-carbon bond. Okay, so if you can make that weaker, you're saving a lot of energy in regeneration. So weaker than a covalent bond, you can go to an electrostatic interaction where you've got positive and negative interacting, and this can be as strong as a covalent bond depending on how big those charges are. But if gases were charged, they wouldn't actually be gases, they'd be solids. Okay, so that's the problem. Gases are all neutral. So this is the situation we're really looking at. We've got neutral gas molecules and we want to try to get them to stick to a surface. Well, if the surface itself can be polarizing, if it itself has some highly polar character, what that can do is induce a dipole. So the gas isn't actually charged, but just the electron cloud shifts so that you can get some of it positive, some of it negative. And that's really the strongest interaction you can hope for. Okay, so if you can do that really well, then maybe that layer of gas will then polarize a next layer of gas, and you'll get strong adsorption. So this is called chemisorption, this is called physisorption, but generally we're talking well under half the strength here.